All right. Hello, everybody. My name is Matt Picklo. I'm a second-year PhD student in the Computational Applied Math program. This project, Improved Discontinuous Galerkin Methods via Post-Processing in a Multi-Resolution Framework, is a part of ongoing research being conducted by my advisor, Dr. Ryan, and myself. So the reason why we care about all those complicated sounding words is that the relevant scales of lots of different physical phenomena can span many orders of magnitude. Consider turbulence and fluid flow, right? Small scale fluid interactions are affecting these large scale structures. You know, a butterfly is flapping its wings, a hurricane appears someplace, right? So if we really want to capture the behavior of these physical phenomena using our numerical techniques, we need to consider all these different scales. Again, large eddy simulation, you have you're looking at large eddies, but these small fluid interactions are going to affect those and affect how good you can approximate them, or how well you can approximate them. So in order to improve these numerical techniques, we need tools that allow us to move information between scales so that we can consider these the behavior of these physical systems on multiple scales. This project is basically about kind of linking together two of them: projection techniques, which allow us to transition between the scales, and post-processing techniques, which allow us to reduce the error during those transitions. So we're doing all this in the framework of discontinuous Galerkin methods. The modal variety for hyperbolic problems are initialized based upon projection. Basically, you're given an initial condition, and you approximate it with a piecewise polynomial basis of some degree. Your approximation is just a linear combination of those functions, and you evolve the coefficients of that linear combination in time according to your PDE. Just using a projection, you can get order p+1 accuracy. If you look at this plot here, this is a linear basis using 8 elements, and we're projecting a sine wave onto it. And basically what we're seeing is that we're capturing the hills and the valleys, but we can still see discontinuities at element interfaces. That's the discontinuous and discontinuous Galerkin methods. Continuity is not enforced between elements. If we use a finer mesh, say 16 elements, not only do we capture the behavior of the sine wave better, but we also can no longer see those discontinuities. They're still there, but they're just out of our ability to see at this scale. So how can we improve these techniques? So there's a thing called a SIAC filter, smoothness increasing, accuracy conserving. And basically, it's this specially designed convolution kernel that we convolve with our approximation to reduce the error. It has these nice properties. It's a linear combination of B-splines. This is so that we choose B-splines so that it has finite support. We don't evaluate this integral over all of R. We only evaluate it over the support. We do the linear combination so that we can choose these coefficients so that our kernel reproduces polynomials under filtering, or under convolution, sorry. This is so that it has nice error properties. Now, here's an example of why we use it. So we can go from order p+1 accuracy to order 2p+1. And this is the absolute error of that same sine wave, but using a piecewise polynomial basis of degree 2 and 40 elements. It oscillates a lot, and though the error is really low at some points, it obtains superconvergence at some points, it is very high elsewhere. What the SIAC filter does is not only does it reduce the error, but it also reduces the oscillations of that error. For this, we're using 2p+1 B-splines of order p+1. So now the question becomes, how do we get a fine mesh approximation out of this? So what we do is we filter our initial condition, we project our initial condition. We then filter it. All of this takes place on the coarse mesh. We then project onto a finer mesh, where we can then filter it again and project it again onto an even finer mesh. And we can keep doing this. It turns out, however, that there are some diminishing returns. So if we consider just the L2 and L infinity errors of this sine function under this procedure, using 2p+1 B-splines of order 1, what we see is that if we just keep projecting the projections onto finer meshes without filtering, the error doesn't change. That's because we're projecting a polynomial of some degree on an element onto a sub-element of that element. So nothing's going to change. Now, if we filter it in between, though, we can actually get a reduced error constant when we project again. If we just keep projecting, though, without filtering, again, it will level off. If we filter between every projection, the error continues to decrease until, again, diminishing returns. It's not going to improve very much. So what is a general framework for moving from coarse to fine? So that gets into this multi-resolution analysis stuff, which is a little bit beyond what I have time to talk about. So the general idea is that, for our purposes, is that if we choose a specific basis, say the orthonormal Legendre polynomials, we can determine we can write our filtered approximation in a new basis. These chi functions, chi left, chi right. These b functions are determined just by our modal coefficients on the coarse mesh and our kernel coefficients. So what we can do, and the reason why there's a left and right, is because depending upon where our filtered point is in the interval, our kernel support will overlap different elements. And so that leads to different functions. So anyway, we have two different forms, one for our filtered approximation, one on the left, one on the right. We then project those forms onto the refined mesh, And so really, we only use information from the portion of the coarse mesh that is becoming an element, or becoming a part of an element on the fine mesh. So really, the projected left filtered approximation is going to become the fine mesh approximation on this I 2j minus 1, and similarly for the right, it's going to be the fine mesh projected filtered approximation is going to become the fine mesh approximation on I sub 2j. And it turns out you can encapsulate all of that within these T sub L and T sub R matrices I derived. Now, and so basically these matrices take coarse modal coefficients, make them fine modal coefficients. So these ideas generalize into higher dimensions. Basically, your projections now, instead of being of one argument, are of two arguments, say in 2D, right? So you project onto polynomials in X and Y. Similarly, our kernel becomes a tensor product kernel. We take a 1D kernel in X, multiply it by a 1D kernel in Y, and we evaluate a two-dimensional convolution. The filtered approximation forms, those special things we derived, those also generalize. Only now, in 2D, we're going to have 4 different ones, depending upon which quadrant you are in your square element. Similarly, in 3D, we're going to have 8, one for each of the octants. And that's just because if you think about it, if you're left or right with respect to one axis, X or Y, right, you're then left or right with respect to the other. And so you have 2 times 2 is equal to 4 in 2D, 2 to the 3 is 8 in 3D. And so that's kind of what's going on there. So in the future, we're hoping to extend this to what's called the L-Sciac filter. Basically, it's a Sciac filter that's aligned with a non-Cartesian axis. That allows you to, I guess, reduce the amount of quadrature sums you're performing, right? Now, we'd also like to generalize this to arbitrary meshes, right? Physical problems do not use nice meshes, and we want these tech tools to be applicable to a wide variety of problems. So we'd like to extend it to them. And then lastly, of course, we'd like to actually apply it to the physical phenomena or physical problems in question and see if we can discover some, or to gain better insight into the behavior of these systems. And of course, references. Thank you so much for listening, and feel free to reach out if you have any questions. Bye.